Right, for our fourth QQT, actually the fourth and the fifth one are kind of going to have the same setup, but they're going to ask different questions. So a box is pressed along a horizontal spring, compressing the spring from its relaxed length. The box is then released and the spring launches the box horizontally along a track that ends in a ramp as shown above. The box has enough speed to leave the ramp and the box reaches a maximum vertical height above the floor. Assume there's negligible friction between the box and the track and air resistance is negative. So K is the spring constant, X is the distance the spring is compressed, M is the mass of the box, theta is the angle of the ramp from the horizontal, and H is the maximum height reached by the box. So those should all be pretty familiar variables, okay? The scenario is repeated using a stiffer spring with a constant that has a greater value for K than the original spring. The stiffer spring is compressed to the same distance X and the same box is used. So for part A, we are going to indicate how using a stiffer spring would affect the maximum height reached by the box and explain why without mathematically deriving a relation for H. So for my money, they actually gave us more information than we needed. They could have just said a stiffer spring. So be ready for that. Realize that a stiffer spring means that K is higher. Okay, so the answer for this, I think it's probably pretty your gut instinct that it's going to go higher, okay? But we need to justify this. And I did it from a conservation of energy standpoint. I said that the energy provided by a spring is, or the energy stored with a spring and mass is 1/2 kx squared. A conservation of energy says that this is converted into kinetic energy, which is equal to 1/2 mv squared. And then the ramp converts that kinetic energy into gravitational potential energy, which is mgh. So by that line of reasoning, whoops, that's not x, k. If k were higher, then this velocity would be higher, resulting in a higher h. So 2 points for part A. 1 point for realizing that a stiffer spring would give a higher velocity, and then 1 point for saying that a higher velocity would give a higher height. So 2 points for part A. For part B, I hope it's getting sort of familiar that they throw this equation that students have figured. H equals sine squared theta times kx squared over 2mg, which may or may not be correct. Is this equation consistent with your claim in part A? Why or why not? So the answer is yes. The answer is yes because K and H are directly proportional. If K increases, then H increases. So 1 point for a yes answer plus what they call an attempt to justify a functional dependence. Hopefully you've heard me say that a few times. Some way of saying by the formula, as this increases, or whatever the relationship is. So 1 point for the yes answer and then trying to relate that back to the formula. And then you get another point for indicating that since K increases, H must increase. I would not say just that H and K are directly proportional. I might start with that, but I think you want to say if H increases, K increases. I think you want to say it that way. So 2 points for part B. So for part C, D, E, and F, we have student 1 and student 2 with their 2 statements. Student 1 says the speed of the block at its maximum height is 0 because the kinetic energy is a minimum at the top of the trajectory. Well, the kinetic energy is certainly at a minimum at the top of the trajectory. So statement 2 is correct. However, statement 1 is incorrect. Statement 1 says the speed of the block at its maximum height is 0. Don't get sucked into that. Yes, the vertical speed is 0, but that horizontal speed is still trucking along at that maximum height. So statement 2 is wrong. Statement 2 is right. Statement 1 is wrong. That is C and D. Student 2 says only the vertical component of the velocity is 0 at the maximum height because the vertical component of the acceleration is 0 at the top of the trajectory. Okay, student 2 started out on the right track. In fact, that was what we just said. Only the vertical component of the velocity is 0 at the maximum height. So statement 1 is correct for student 2. However, The vertical component of the acceleration is not 0 at the top of the trajectory. The vertical component of the acceleration is always g the entire time. So statement 2 is incorrect. So for C, D, E, and F, 1 point each for the right answer and for no wrong answers. I think I may not have been clear on that before. Someone asked to clarify, so I apologize for that. I think those questions are just 1 point each. Sorry, I know they're just 1 point each for this question. I think in general they're 1 point each. Okay, part G asks us to consider the system consisting of the box and the spring, but not Earth. So here's what I'm thinking. I can use kinetic energy because that's just the box. I can use the spring potential because that's the box and the spring. But gravity's external to the system. So gravity's going to do external work on the box. How does the energy of the system when the spring is fully compressed compare to the energy of the system at the moment immediately before the box hits the ground? Okay, the answer is they're equal. Okay, so you get 1 point for saying that. Here's the explanation here. Initially, the box has 1/2 kx squared. Okay, and then at the end of this, it has 1/2 mv squared. The net work done by gravity on the box is going to be 0 because it returns to its original height, right? We start on the ground and we end back on the ground. So regardless of whether that's h equals 0 or some other value, there's no external work done by gravity. Or I should say the net work is 0. Gravity does negative work as it's on its way up, and gravity does positive work when it's on its way down, but the net work is 0. So you get a point for saying that the energy at both points is the same. You get 1 point for saying that there's mechanical energy in the spring, or you could say that the box returns to the same height. Okay, so you could say the box returns to the same height, so no external work is done, so the energy is the same. You could say that for 1 point. Or you could say the stored energy in the spring, 1/2 kx squared, is equal to the kinetic energy that the box has right before it lands. That's the 1/2 mv squared. Then the third point says 1 point for saying that just before the box lands, all the energy is kinetic and so none is lost. So you get 1 point for the right answer, the saying that they're the same. 1 point for saying there's mechanical energy in the box spring combo at the beginning. 1 point for saying that there is kinetic energy in the box at the end. Or instead of those 2 points, you could say, since the box returns to its original height, no external work is done by gravity, and therefore the answer is equal. So 3 points for part G, either way you slice it. All right, so for part H, they say, well, what if we added some friction? Right? If the friction between the track and the box were not negligible, state one way in which the setup could be changed so that the maximum height of the box was the same as in the original setup. So hopefully you have reasons that if there's friction and we don't change anything else, H is going to decrease. So let's talk about how we could possibly get back to our original H, okay? And there are a few ways you could do it. You could use a stiffer spring so that the box had a larger velocity when it leaves the spring and therefore could maybe get back to the original height. You could make the ramp a little bit steeper, okay, so that more of that initial velocity upon launch was in the Y direction. We could go higher that way. Or you could also say use a lighter box so that my 1/2 mv squared after launch, my V is a little bit higher. So those 3 ways. When they tell you to say name one way, do not list every way you can think of, okay? If any of those are wrong, you get no points for that, okay? So don't try to hedge your bets. Don't say everything you can think of hoping that something's right because you will get no credit, okay? If you're wondering, if you've got 2 ideas and you're wondering, pick the one that you're more sure is right. But just a little advice, do not ever on these FRQs, like throw everything you know at it and see if something sticks, because that's a recipe for failure. So 1 point for part H, indicate a valid change that would increase the height. Finally, part I, how would the slope of the graph be different? Oops, I'm sorry, I forgot to read the part above the graph. The graph below shows the horizontal component of the displacement of the box as a function of time. The graph represents the entire time the box is in the air after it's launched from the ramp. So it's pretty obvious that we have a delta x equals vx t situation here. It's the slope is a straight line, the horizontal speed is constant, okay? How would the slope be different if the ramp angle were larger than theta, but less than 90 degrees? So let's say this is our original angle here, okay? So my Vx then is V cosine theta, right? Now, if the launch were steeper, right, but not 90, okay, but not 90. Now my Vx is again V cosine theta, but as theta increases in the first quadrant, the cosine decreases. So this number here is going to be smaller than this number, okay? Our x component of velocity is going to be smaller. So the slope of this line is going to be lesser, okay? We're not going to have to graph this, but they certainly could ask you, would the slope be greater or less than? And the slope would be smaller. So 3 points for part I, 1 point for saying the slope would be smaller, 1 point for saying that the horizontal component of the velocity decreases as theta increases, and 1 point for saying that the slope of the graph is equal to the velocity of the block. So 3 points for I. So hopefully you were able to get most of that. I think this is a pretty representative QQT, and I feel like they're getting easier. I hope you feel that way too.